Okay, thank you very, very much, Paula, for that very nice introduction. So I can skip the first two slides here because you already mentioned the most important things. You see, hopefully you can see my video. I'm not sure I can see it right now. And this is where I live, actually. Yes, you should see, if you see my face, you should see the same background on Zoom. The agenda of today's talk is 4 points: measuring test size. Test size matters, the benchmarking process for test size, and some conclusions. The point is indeed, test size is something a little bit different from what we usually do when we measure functional size, because functional size very often we measure it in the view of getting information: how big is some software, how much will it cost, how long does it take to develop it. Test size is something different. Yes, I heard a voice in peeping, but that was not the question. Okay, goals of this presentation: understand how to test size based on Cosmic. I'm not sure. Can you hear me again?
Apologies, Thomas. I was trying to mute the others in the background, and we've lost the last 10 seconds of what you said. So if you can go back, please.
Okay. So I'm coming back to the goals of this presentation. So goal number 1 is to understand how to size tests. This is based on Cosmic. I'll come to IFBook as well. Get aware of the economic importance of test benchmarking, because I think personally this is the future of ISBSG, because test benchmarking is much more important than cost benchmarking in some respects if we look at the future. And finally get introduced to this notion of autonomous testing for complex software-intensive systems. So let me start here. First of all, I should say I unfortunately first named the presentation test density. Actually, this cannot be true, because a density refers always to some finite number of possible opportunities, and therefore it cannot be test density, but it must be test intensity. However, we will see we can speak about defect density safely. But it is not so easy, and it is not so clear, at least not in the testing community. Current testing community is rather referring to lines of code instead of anything measurable, reasonable, or say a metric. Lines of code is not a metric. Lines of code is something which comes from the past, is probably today no longer valid, and so on. But we will come to that. Test coverage is the other thing that we should actually look after, because it is very important to have a comparable notion of test coverage for such things like autonomous cars or anything that can harm people when upon failure. And this is more and more the case for software. So research questions here is: how do we actually define such things like defect density or test coverage if we don't have any code? It is very often the case. We use a service from the cloud, but we have to test it. Or a service in general may not come with anything that we can compare with code. And then even more important, artificial intelligence. Imagine artificial intelligence. This is not something, an algorithm that you code. Artificial intelligence is a machine that can learn. And the functionality of that machine has been by learning right behavior. Unfortunately, when you learn some behavior, you can also unlearn it. So System testing refers to functionality, not code. This is the first thing that we should agree on. It is absolutely nonsense to speak about test density or a coverage when we refer to code. We should refer to the functionality. However, how can we measure functionality? Well, we have a very good answer, which is very well tested. So this is just to show. I mean, we know how code looks like, but this is not what we actually gonna test. So, what is a defect? Here we have our Mr. Tester. He sees a number of bugs. They are coming around and playing around. I hope you can see it here through the video, through the internet. And now you should find out how many bugs do we have. How should we count that? By counting the size of defect repositories, by the number of entries in that repositories. Is that anything that is worth being counted? Well, we prefer to use functional size. Functional size you can, for instance, represent here by the data movements map. The tester can walk the data movements when planning or executing tests. Hope this works as well. You see Mr. Tester here walking through a data movement. We have data movements defined by the Cosmic International Standard as entries, exit, reads, and writes. So that can be used to, for instance, do software testing, visually represent as a game. And now the point with IFBook. We had this discussion with Pierre and Christian Green, the president of IFBook, already some years ago. Can we use also IFBook to size testing? And today my answer is yes, you can. However, it's much more complicated. It doesn't look as nice as with Cosmic. And you have to address the problems that Marcello has shown us for microservices. How do you do boundaries? If you draw boundaries around each test case, then you definitely will have a huge problem with multiple data elements counting. So you have to find another way, which is not totally explained right now in the IFBook manual. But I believe it can be done with some allowances for not being completely, capable or compliant to the WIM and the GAM, that is the standards that apply for having a real metric. In this case, for instance, one of the difficulties is I tried to use or to show the same application as before with Cosmic, and here we see, for instance, that one of the EOs here does not use any ILF, so it's an EO without FDRs linked to any of the other objects. Can happen with IFBook, sure, but it's not so nice for the tester to walk on it. So this is why we continue with Cosmic. Here you see, for instance, our tester has found one bug. It's one bug because he has found it on the second data movement that he walked with his test case. And he can now start counting bugs with the same metric as counting functional size, namely Cosmic. So you have functional size. You can say test size is the number of data movements executed in test cases. So you can very simply, because Cosmic is actually a metric which fulfills the WIM and the GAM. Therefore, you can simply add the test cases and get a number for the test size. This is actually the total number of data movements executed when running all the tests. Something very simple. A test story is a collection of data cases, test cases that aim at certain functional user stories. Test intensity is the total test size divided by total functional size. And obviously, because you can have as many test stories as you want, you can increase the number of tests as many as you need, and therefore increase test intensity up to a certain point that fulfills your need. And the defect count is the number of data movements which is affected by some defect detected in a test story. So you should take a precondition similar as we have in Cosmic, not to count defects, the same defect twice if detected by two different test cases within the same test story. But this is already then a little bit more complicated for actually defining a true way of sizing tests and defects. Okay, here you see how every data movement provides one opportunity for detecting a defect in a test case. That is, you can first find the first defect, then the next defect. After fixing the other defects, the third, then the fourth, and the fifth. So this is important because it means that the total number of opportunities for a defect is actually equal to test size. And this is wonderful because for the first time, you can apply Six Sigma, who is actually referring to the defects per million opportunities in order to measure the way how well, how secure, how reliable any system is. And using functional sizing, we can do that for software as well. And every other attempt which has been tried in the past of doing Six Sigma for software, I'll say, is, in my view, a little bit false. Okay, standard definitions apply. Defect density is defect count divided by total test size. Typical Six Sigma software here has Six Sigma with 3.4 defects per million opportunities. That's fairly few. And in the 80s, we were already able to write Six Sigma, to write software which achieved something like 5.5 sigma. The Six Sigma was simply too expensive. So remember the Raven when counting defects. You know the Raven, I hope. His will tell you do not count more than you really must, namely one defect per one data movement and one test story, never more. So this is now advertisement. Test size matters. This is not something academic. A very famous example has been done in the 19th century where, well, it was early 19th century or even late 18th even, where Mr. Watts has found that for marketing his steam machines, he needed actually a metric that explains how much better steam machines are compared to the horses that before were usually done for doing the work. This metric proved to be very successful and made Mr. Watts the inventor and rich inventor of steam machines and steam engines, and even then later the steam locomotives. That was a metric, and the metric made the difference and started this steam machinery to grow in all the world. Today, we have no metrics in use for things like how well does the software work in our cars, for instance. Almost every modern car, say, starting from a certain level, middle class, has now an advanced driver assistance system, ADAS, that actually replaces a little bit the task for the driver and also takes some burden off and turns the burden back on the supplier of software, because the supplier of software is probably liable for the quality of his software. So he should actually not only do continuous integration, continuous delivery or deployment, he should also do continuous testing. And how many of our automotive suppliers do that? Well, you see, we have a lot to do. In automotive, the size of the software, which is, for instance, in a Tesla, as we have seen with Harold before, is absolutely something that really matters. This is of relevance. The number of tests that have been used to make sure that the Tesla is a reliable car, doesn't burn up in accidents, and recognizes when turning left and right and avoiding collisions, is a precondition for success of that kind of systems. It's not only with automotive, but in automotive it is apparent and is probably the first area where it really has an impact. We have other quality requirements which must be tested and actually have a test size. And this is privacy, safety, which safety, for instance, in an ADAS becomes then from a non-functional to a functional requirement. Software metrics are something for the public. This is not something for the technicians, not even alone for the, say, for the controllers. This is for the public. We need to explain how well we are. And if we don't do that, then nobody will pay us for our tests. So let's come to the benchmarking process. I think I have still some 10 minutes left, or 15 minutes. So naturally, the question is, if I say testing, this is expensive, and say the today's methods of doing tests, developing test cases, are absolutely ineffective. Just imagine you have, say, 1,000 user stories would make up for 5,000 to 10,000 test stories, and then you do test cases, a dozen per test story. These are numbers which you can't handle easily. We have a famous example here, for instance, is a wonderful train that now finally starts running after 7 years of commissioning. Actually, they say this is commissioning. That was not commissioning, actually. That was an attempt of testing. It was testing by running, by just executing the functions and looking after them, and hopefully you found the bugs or not. If you don't know how many you didn't, probably after 7 years you have found enough bugs and removed bugs such that you can let people using those trains. Customers, on the other hand, they expect naturally no defects, Six Sigma. Very simple. That's what customers expect. And in fact, if you're sitting into an autonomous car, you probably better expect Six Sigma. Or today, if you take a plane, there you already have something like Six Sigma. But not measured, it's just believed. Well, this is our problem here. We have millions of test cases. And there is no way that testers can ever provide them by manual methods. What we need is a fountain for test cases, an automatic test case generator that combines new test cases, maybe from existing ones, maybe from the initial unit tests, and does that probably as long as needed. And we need a metric to say how long means needed. This we call autonomous real-time testing. Autonomous means that we use modern techniques to generate test cases automatically. So we do not only do automatic tests, we also do automatic test case generation. This can be achieved, and Paula mentioned it, is quality function deployment occupation of mine. Yes, it's quality function deployment. We need to focus on user values, because otherwise we cannot decide whether a test case is relevant or not. You do that by using transfer functions. I will not explain transfer functions today, because I did that already in other talks, and I have written a book on it, and I hope transfer functions are meanwhile fairly known, at least to this excellent audience that we have today. Just one thing that I wanted to explain: how do you actually match those test cases with the user stories, that is the requirements? It is basically very simple, but it is not straightforward. You count data movements that are executed in test cases with some relevance to user stories. If you have actually to identify that manually or by methods of requirements engineering, which part of my applications refer to what user stories. Otherwise, it won't work. But I think a little bit of professional requirements engineering today is at least done in most cases, or in many cases, or I hope so. So the transfer function now says, well, if you have a goal set for user stories, then you can say, how well does our test stories actually meet the goal stories that we get for user stories? That is, how well do the test cases cover the requirements of the user? That can be measured. It must be measured using something reasonable, so like counting data movements, which you can do naturally automatically after you identified the relevance. And the conversions gap indicates how well did you do it. So 0.11 means, well, about 11% deviation in direction when you look after these profiles as vectors in a multidimensional vector space. Then here we have 6 dimensions. Then convergence gap simply means how well does the direction match. Naturally, it can be that it doesn't match at all, but usually we should bring it to a match. The next question naturally is, how do we know what is relevant? So having a goal profile is not for free. Agilists usually have a goal profile for their user stories because they need it for prioritizing the next sprint. But even in agile development, finding a goal profile which is really expressing the needs of the customer is not something that is easy to find. And for testing, not at all. However, it is very important, because if we can keep the convergence gap close to 0, that would give us a means in our test case fountain to select those test cases that add to closing the convergence gap to 0. That's basically what we do. And I'll show you here in a very simple example, also taking a little bit from automatic car driving. Here, for instance, we have here 5 user values which give us the importance for the customer. So he needs to drive fast, he needs to drive safe, and this gives a profile which helps us to identify those data movements that actually support those car user needs. This gives the first transfer function with a first convergence gap, telling us whether our solution that we found actually matches user needs. Something technical, which we very often do. Normally in Six Sigma, this is probably not a standard practice, but it can be done, and it pays off. Again, the numbers in our transfer function actually arise from counting data movements. So it's functional size. Now we can do that in a second step. We can take this profile which we got for the user stories, or we can ask our agilists whether they have a profile for the user stories. That's done as well. But then we still need to identify which data movement belongs to what user story. Otherwise, we can't get test coverage automatically. Here we have automatically test coverage, and so we can decide which test cases to take, because the numbers here must be such that the test stories actually fulfill the needs of the user stories expressed in the user stories. Here you can see how this evolves. We have our test case generator, our fountain, providing more tests here. For instance, we add here more tests. We can here add more tests. So actually, we can actually let our test coverage grow up to the effect that we are satisfied with it. And when are we satisfied? We are then satisfied as soon as we are better than competition. So this is a competitive measure used for selling our software. So let's come to conclusions. Hope I'm in time. Actually, I didn't tell you how you do autonomous real-time testing, how you do generating test cases. You need combinatorial logic. Combinatorial logic is not something that is on everybody's list when you get engineer. It is a discipline from mathematics that has been developed around 100 years ago. And probably not yet with any intent of using it economically, but it has an economic use, and it is very interesting how it is developed. I would recommend to watch this. Basically, it is a combinatorial logic allows us to combine tests in such a way that from an existing starting set of tests, we can create new tests. And with the convergence gap, we can decide whether we use those new tests or not. That allows us to do autonomous real-time testing based on software metrics. This is not something that I would call an easy job to do, but it is probably very promising for the future. Just a few other conclusions, important again. As I said in the beginning, you do not need to know implementation or code of our software. All you need to know are the requirements, are the user needs, and you need to have a model for our software that is From the granularity, it is sufficient to have a data movement map. You can do that on any level that you actually need. You know, those cosmic levels that you can use. In many cases, it is absolutely sufficient to use a level, say, around Kubernetes, around linking microservices from one to another. That naturally gives not a very big functional size, but it can already be used to address and measure actually the safety or reliability requirements in our software regarding privacy. You can test neural networks and perceptron if they were ordinary software simply by measuring the requirements you have to those neural networks. Well, perceptron is a very old concept. Today we have those machines that actually do searching from Google. Naturally, the point is you must do it continuously because learning systems keep changing. They do not only learn, they also unlearn. And this is an application of artificial intelligence to operations real-time everywhere and also to testing. However, you should remember that artificial intelligence is not intelligent, it is big data, but it deals with variations. Software testing is, in my belief, the horsepower of digital economy. That is what? Simply the same as we had for years with the mechanical engineering, horsepower, how powerful are our cars? This is software testing. And this means sizing tests. As I said, I prefer cosmic. You can try to use others if you really want. And in any case, you need the voice of the customer techniques to measure relevance. So now I'm open to questions. I brought 2 books about it if you dare to go more into details to it. And I'm here now for any questions.
Okay, Thomas, we have one question. It's from Stavros. Setting aside the client maturity, how long does it take, in your experience, to implement a sustained such Six Sigma program? What's the magnitude of cost? Have you seen measured business cases, how high the real return or invest is?
Indeed, I should really say that the experience with measuring software and bringing it to Six Sigma, that was a very early experience in the early 90s, where we managed to have software up to some 5.5 Sigma, and this became then very, very successful. It was at the time the standard for POS, for point of sale software. Later, I say that or Paolo said that in my short introduction, we had several. I had the opportunity to help several enterprises to really bring their software up to levels. We measured the size, we measured the testings, we did almost, except that at the time that wasn't yet automated. This is due to today's large software. The software there were some 5,000 function points, and you could therefore manage tests. And this didn't cost something, yes, but the revenue was that you had become the world leader on it. Very simple. So I would. It's difficult to say whether well it's, you can say it pays off, yes, but how much, I can't answer that.
Okay, thanks, Thomas. Okay, thank you very much. And our next presenter